click to record just because I have been known to forget to do that. My clock says straight up 12 noon, and I'd like to welcome everybody to the Beef on Dairy Dialogue webinar series. It's an extension of the annual Dairy Beef Short Course held in conjunction with the Central Plains Dairy Expo each March. The short course is the longest running program focusing on steers with dairy genetics in the U.S., with 15 years of continuous programming. The short course is sponsored by the I-29 University, a consortium of extension specialists from Iowa State University, University of Minnesota, University of Nebraska at Lincoln, and South Dakota State University. The Beef on Dairy Dialogue series continues today with Dr. Blake Foraker, an assistant professor in meat science at Texas Tech University, who'll be discussing how dairy cattle are inherently more muscling deficient than beef cattle, which influences their value in the beef supply chain. He will focus on how beef on dairy cattle perform for carcass yield compared to other types of cattle. This presentation will also highlight the innovative methods being evaluated to better assess carcass yield on all cattle types. Dr. Foraker is an assistant professor and holds a BS in animal science from Kansas State, an MS in meat science from Colorado State, and a Ph.D. in meat science from Texas Tech. He spent 2 years on faculty at Washington State University before returning to a faculty position at Texas Tech, where he serves as a coach for the meat judging and meat animal evaluation teams. His research expertise pertains to meat animal growth, carcass composition, and eating quality. He has extensively studied the growth, carcass yield, and meat quality of beef on dairy crossbreds, as well as innovative methods of carcass yield determination. As I always say, Dr. Foraker, the podium is yours.
All right. Well, thank you, Fred. It's a pleasure to present to the group today and share some things about what we've known for some time now relative to beef on dairy, and then we're going to quickly transition into some pretty innovative and forward-thinking concepts that are much bigger than beef on dairy, and I think will continue to shape all of the beef industry, no matter dairy influence or not, as we move forward here. So some of this work that I'm going to present today will has some age to it, and so I know we're talking present and future, and so I really probably should have put past, present, and future. But some of the data is as old as 5 years. So firstly, I want to kind of give a recap of what the focus of my dissertation work during my PhD program at Texas Tech comprised of. That'll kind of be the bulk of the front end of the data that we show here, basically with the point that there were a lot of things, beef on dairy opened up a new line of thinking, if you will, for myself and many researchers here within our program at Texas Tech. And of course, we're on the meat science side. And so as meatheads, we studied everything, not only from carcass composition, but to the eating quality of the steaks, the growth of the live animal, the muscle biology of those animals. You see the photo of the liver abscess there in the bottom left, because we've looked at that as well. And so, of course, that in and of itself could be an entire presentation. with seemingly where we're at as an industry is lots of variables that going into affecting things like liver abscesses. But today, one of the things that we're going to focus on is carcass yield. And one of the major takeaways from my work in 2019, 2020, 2021 during my graduate work was uh, overcoming some muscling deficiencies of beef on dairy crosses. We know that the dairy influence is has a dilatory effect when it comes to muscle logically, and but what we've found out is there are ways to overcome that in our industry, and in fact, ways to make the beef on dairy cross animal extraordinarily valuable, if not as valuable as a native beef animal when it comes to carcass yield. One thing I want to make sure that's very clear before we start this presentation focused on carcass yield is that what I'm talking about today is not dressing percentage. And so from a feed yard perspective, oftentimes they'll talk about, a pen of cattle yielded 63%, 64%, 65. That's not what we're talking about here today. In fact, in my opinion, dressing percentage is quite a poor predictor of the abundance of the edible products that we are producing from cattle. And so this is just one plot, one set of data that demonstrates just that, where we've got dressing percentage on the x-axis and the actual percentage of the carcass that is comprised as muscle on the y-axis. And so certainly you can see some animals that may be considered outliers or extremes, if you will, on the low end of dressing percentage and the high end of carcass muscle percentage. But even if you focus within our what we might consider traditional or normal range of dressing percentage from 62 to 66, you can see that the relationship there to the actual abundance of edible tissue or muscle tissue in the carcass is quite low. And so just to put that clarification out, we're not talking about dressing percentage today. We're talking about the abundance of the carcass that's comprised of edible tissue. So I'm gonna kind of summarize in a few slides here some takeaways from some key studies that we learned from beef on dairy. Again, kind of using beef on dairy as a model and thinking about things a little bit differently within this population. We're going to then be able to extrapolate that to the broader beef population and how we used beef on dairy to identify some challenges as it pertains to the measurement of carcass yield within our modern day beef industry. And so within this particular study, this actually wasn't even designed originally as a yield study at all. It was funded by the Beef Checkoff to evaluate eating quality differences, so tenderness, flavor, juiciness differences between different phenotypes of beef on dairy cattle. And we don't even show the slide anymore, but there were no differences in eating quality depending on how those animals looked visually, whether they looked more beef type or whether they looked like a black-hided Holstein. And we had some hypothesis going into the study preemptively from some previous work done in the 90s on Brahman influenced cattle, that those that, even of equal breed composition, those animals that looked more Brahman ate more Brahman and were tougher. We thought that the same might hold true in the dairy influenced cattle, and in fact, it did not. So the takeaway from that study was, as an industry, let's make these dairy crosses as beef-like as possible from a conversion and efficiency and a muscularity standpoint. Let's maximize their beef traits, knowing that we're not going to have a deleterious effect on eating quality. Well, simultaneous in doing that, we measured all of the traditional carcass traits. So we were using a live muscling score that you see in the top row there to segment those cattle into their phenotype groups on a scale from fully dairy type to fully beef type. So we had 4 treatment groups. And so by design, live muscling score was different. But what you'll note there in the second row is that ribeye area wasn't different at all between any of those phenotype groups. And what that demonstrated, which by the way, all of these cattle were at a constant live weight. So live weight and carcass weight did not differ between these phenotype groups. What this demonstrated is that the current metrics that we have in our industry to measure muscularity from an objective standpoint, that being ribeye area, doesn't work. And it certainly didn't work within this population of 650 calves. And so that was concerning to us moving forward here, knowing that this dairy influenced population is inherently lighter muscled. How do producers overcome those obstacles to try to maximize meat yield within these cattle types that are being discounted at the packer? And one of those reasons that they're being discounted is because of a lower muscle to bone ratio. So we conducted this study to better characterize the actual subprimal yield differences between 4 cattle types. So the 2 primary cattle types that you see on the top there would be the native Angus steer or native beef animal, and then the conventional Holstein dairy type animal, and then 2 subgroups of beef on dairy crosses in the bottom 2 photos there. So we characterized those. We went within contemporary lots and identified high yielding crosses and low yielding crosses, and then measured all of the different components that came from those carcasses in the form of subprimals. So things like the strip loin, the tri-tip, all different kinds of trimmings and the various lean points of those trimmings, the components of fat and the components of bone that came from every one of those carcasses. So a study that was comprised of approximately 200 cattle, conducted real time, so at line speed at a large commercial packing facility. Again, all in an effort to not only characterize beef on dairy crosses and the average beef on dairy cross relative to their parental breed types, but also what makes the high yielding crosses within a contemporary lot different from the low yielding crosses, and how much different really are they? And so these are the results, the data that's shown here. So we've segmented these data by subprimals, fat, and bone portions of the carcass. They're expressed as a percentage of the hog carcass weight, and the bars that you see with the mean represented by the dot represents the difference from 0 of the overall population, or the difference from the mean of all cattle types. So the reason why we're not showing the actual values here is to not disclose any proprietary information of the particular packing plant that we collaborated with to conduct this work. It's very highly proprietary, and so we don't want to share that info. But we were ultimately interested in comparing breed types, and we can do that as a difference from the mean. And so what you'll see is very large differences in the percentage of bone generated from these various cattle types, a stair-step effect, if you will, where the dairy cattle had the greatest amount of bone, the beef cattle had the least amount of bone. Really no surprise there. You do see in the subprimal portion that the high-yielding beef on dairy crosses actually weren't different in the percentage of subprimals that they produced from the native beef animals. So we're going to then dive deeper into that subprimal portion here and assign some dollar metrics to those subprimals, and I'll show you the differences between cattle types. So if you just focus on these numbers here in the top left portion of your screen, these are the differences in dollars per hundredweight from the overall mean cutout value of the study. And so what you'll see is that the high yielding beef on dairy crosses actually generated the highest cutout value in the entire study. In fact, a statistically greater cutout value than the native beef animal, which rated second, and then low yielding beef on dairy crosses followed by the conventional Holstein steer producing the lowest cutout value. So if we just make some comparisons, as you draw your attention to the top right hand information presented on the screen here, and I kind of just like to compare beef versus dairy, the difference or the advantage in cutout value of beef as opposed to dairy was about $11.42 per hundredweight. If we compare the average beef on dairy animal, skip 4 lines down, compare the average beef on dairy carcass to the conventional Holstein steer, you can see that difference is nearly as much as the conventional beef versus dairy animal. And so as we talk about sustainability and what the beef on dairy cross has done for our industry, I think it's important to remember that the displacement of that Holstein population with the beef on dairy cross is substantial for many reasons. And I'm sure you've heard talks about the conversions at the feedlot and the higher dressing percentages, but even at the carcass level, the cutout value of the average beef on dairy animal as opposed to the Holstein steer is substantial because we're getting a higher percentage of subprimals out of those carcasses. Now, there's an important disclaimer here, and I've highlighted it here in the bottom left-hand portion of this screen. And I would contend that today, I don't know if you went into a packing plant, conducted the same study, that you get the same results, mainly because I believe that feeders are feeding dairy crosses too fat in today's programs, and they're being incentivized to do that predominantly because of carcass weight and lack of penalty for yield grade 4s and 5s. We're going to talk more about that as we progress into the presentation, but it's important to note that we selected the cattle for this study at averages for hot carcass weight and 12th rib fat thickness for their cattle type. And so across millions of data points, we said, okay, the average 12th rib fat thickness for the native beef animal is somewhere around 55 hundredths of back fat. And so we selected within one standard deviation of that back fat thickness for that cattle type. We did the same for the dairy crosses. Logically, at the time, they were being harvested at a much leaner endpoint, somewhere around 4/10 to 4,500 hundredths of back fat. And then the dairy animal, straight bred dairy animals, of course, were the leanest, around 3/10 of an inch. The point is as we extract these data and interpret what they might mean in a more modern population. Again, these data at this point are 4 years old. If you're feeding dairy crosses greater than 6/10 and certainly closer to, if there's closer to 7 or 8/10 of back fat on average, you're feeding any yield advantage that they may have ever had out of them because they're simply too fat. Because that is the average, 7/10 is the average back fat thickness of the native beef animal. And so it's a real concern that I see in today's industry relative to the beef on dairy cross and any potential that they may have had relative to carcass yield to begin with. Again, I want to point out, though, that the takeaway is properly managed high yielding beef on dairy crosses, so long as they're lean over the rib and have some muscle, can be just as, if not more profitable from a carcass cutout value standpoint than native beef animals. And so then you might ask yourself, what characteristics drove the biggest differences between high yielding and low yielding beef on dairy crosses? So in other words, what specific traits mattered? Because we're going to talk about in the next couple of slides how the trait of yield grade perhaps is not a great predictor of what we're measuring here in the form of carcass yield. We've already demonstrated in a previous study that ribeye area in and of itself was not a good measure of carcass muscularity. So what did these data generated from a packing plant tell us relative to the traits that matter in driving cutout value, which again is the value that the packer is making? And they're, again, only going to pay on the front end for those animals as much as what they're able to profit on the back end. And so what I've done here is within each of the 7 primals of the carcass, I've separated the portions of muscle, fat, and bone into ratios. And so the black bars represent the muscle to fat ratio within each of those 7 primals. And then the red bars represent the muscle to bone ratios within each primal. And effectively, these ratios would explain all of the variations in tissue composition that would contribute to differences in overall yield. And so they've been standardized such that a 1 unit change in, for example, muscle to bone of the brisket is standardized to an equivalent change in 1 unit to, for example, muscle to fat of the loin, so that we can compare them on an apples to apples basis. And what these data demonstrate is that the 2 traits that drive carcass cutout value differences between high yielding and low yielding crosses most distinctly is number one, the muscle to bone ratio of the round. So, in other words, animals that have a very muscular round are going to increase carcass cutout value fairly substantially relative to other carcass components. And then second to that is muscle to fat of the rib, meaning that those animals that have a low portion of that denominator of that muscle to fat ratio, or in other words, are lean over the rib, that's the second most predominant driving factor in increasing carcass cutout value. And so if we focus on those two traits, effectively we should be able to maximize the potential for cutout value from carcasses of these beef on dairy crosses. So number one trait here, just to highlight again, is muscling in the round. And number two is leanness over the rib. We have a pretty effective metric to measure leanness over the rib in the form of 12th rib fat thickness. But when it comes to muscularity of the round, we've demonstrated data that shows that ribeye area muscling is not, in fact, related at all to muscling in the round. And so that kind of creates a predicament as we attempt to make these beef on dairy crosses better from a carcass yield standpoint. This is another depiction of those same carcasses in that study, expressed in a form of yield grade on the x-axis here. So I computed yield grade for all 200 of those cattle. And then I've related that to cutout value, or again, the value that the packer is obtaining from selling the boxed beef at the back end of the plant. And what this demonstrates is that relationship between yield grade, which again was intended and designed to predict the percentage of boneless, closely trimmed retail cuts from the carcass, is in fact quite poorly related to the value that the packers are getting for the abundance of those cuts going out the back end of the plant. This is another similar type summary with some additional data done by another graduate student here at Texas Tech, where they've plotted yield grade against subprimal yield, or the percentage of the carcass going into the box at the back end of the plant. Then they've accounted for cattle types. So they've created 3 different regression equations. And you can see that the R-squared values get a little bit better, particularly in the case of the conventional beef cattle, but still not great, explaining less than 40% of the variability in carcass yield. The fact of the matter is, yield grade doesn't work in modern day cattle genetics. And I could spend an entire presentation breaking down all of the different components of the yield grade and why it doesn't work. I'll just skim over it real quickly and then transition into, again, using beef on dairy as a model. We kind of figured this out with this cattle population. We've extrapolated it to all cattle populations, including native beef type cattle. And then I'll show some innovative things that we're doing to try to combat this problem. So yield grade's outdated. We understand this. We know that the components that go into yield grade are these 4 traits, but it's also important to understand that Mr. Murphy, the scientist at the time at Texas A&M that designed the equation, evaluated a whole host of other traits that didn't go into that equation that perhaps are relevant today. Things like round circumference and chuck dimensions and carcass length. It's also important to note that another reason why yield grade doesn't work is because it was designed from a sample of cattle where more than half of them, 82 of the 162, had a carcass weight less than 600 pounds. And so in an industry today where average carcass weight is well over 900 pounds, I think it's pretty easy to see why something needs to be done to solve this issue. These are yield grades over time of, again, all cattle types across the industry over the past approximately 45 years. And so you can see that today about 1 in every 5 carcasses is a yield grade 4 or 5 carcass in our industry, or what might be considered unacceptable on the yield grade scale. You also see concurrently in the background of this plot, the increase in carcass weight, nearly 5 pounds per year, which again is concurrently happening with an increase in yield grade fours and fives. So to say that the increase in carcass weight is entirely due to an increase in edible portion is not entirely true, because quite simply, those cattle that are producing heavier carcasses seemingly are also much fatter as well. So I challenge, with the increase in carcass weight, is that just an increase in carcass fatness and not actually edible tissue that's ending up in our beef supply chain? But you might say, well, why do we care today? Because I'm getting paid to make carcasses that are bigger and that grade really well from a quality grading standpoint. Why do I care if they're fat? Why do I care if they're yield grade fours and fives? And you're exactly correct in making those statements and comments. And we have these conversations with producers all the time, that you have to do in the current market what the signals are telling you to do. And the signals today are telling you to make cattle bigger and to make cattle fatter and to make cattle that are very high quality, and essentially with disregard to yield grade fours and fives. And that transition happened probably around the 2016, 2017 era, and that's what this plot shows here. So this plot is the combination of the premium and discount associated with the best for yield grade, so yield grade ones and twos, with the worst for quality grade, so select. So yield grade one selects represented by the blue bar here, and then yield grade two selects are represented by the red bar. So I'm again getting a premium for yield grade one and two, and then a discount for select. And so I'm adding those two things together. And then I'm doing the same thing for the worst for yield grade, but the best for quality grade. So getting the discount for a yield grade four, adding it to the premium for prime, that represents the gray bar, and then doing the same thing for yield grade five primes as well. And so what you can see there is a divergence over the last 8 or so years of where really all our industry is doing is incentivizing quality grade and weight, and really not appropriately accounting for a yield grade one or two, or rewarding a yield grade one or two, mainly because we know that equation is ineffective. So I was standing on the line one day in a packing plant, and a lot of cattle came through, and I just started taking these pictures. And this comes, we can sit here today and say, look, we're getting paid to make cattle fatter. We're getting paid to make them high quality. We're getting paid to make them heavy. So why should we change anything? And I think it comes down to a more of a philosophical discussion. And there's no doubt about it that the packers will start to reward leaner, more muscular cattle that are higher yielding as we get out of this cattle cycle. And this is why this is relevant to this beef on dairy discussion. Right now, packers are paying for whatever they can get into the plant, right? And because cattle numbers are so short, and we know that beef on dairy as a consist of the population is a very integral part to the beef supply numbers entering the packing chain right now. But will it be sustainable to continue to make cattle bigger and fatter for decades to come? And I don't believe that is the case. And here's the numbers to go behind that. So Dr. Kristen Hales, one of my colleagues on faculty here, conducted this study, I guess, a couple of years ago, and presented it at our Beef on Dairy Symposium to demonstrate what the cost of fat is in our industry. So she compared cattle that were fed 180 days versus those that were fed 220 days. So effectively, in those last 42 days, depositing fat and weight. In fact, in those 42 days, depositing 11 times more fat than protein. And we know that protein tissue gain is 4 times as efficient as fat gain, or in other words, fat gain is a quarter as efficient as what protein gain is. And so we're depositing, much more fat at a much greater cost than what we are protein at the end of the finishing phase here. She then equated that to, from a sustainability standpoint, what were the inputs required in those additional 42 days to put on 11 times more fat? Well, it was 630 pounds more steam flake corn. And what is the input requirement from a water standpoint to produce that corn? Well, it's 45,000 gallons of water just to feed an animal an additional 42 days. And so I think that so we talk about making cattle fatter and continuing to make cattle fatter with the simple goal of chasing carcass weight. It's not really providing a very sustainable image for our industry moving forward here. And so something has to be done. And so this is kind of as I graduated from my program here at Tech 3 years ago, went on to take a faculty job at Washington State. Simultaneous to that, my mentor at Texas Tech here, Dale Warner, was also working on some similar type things. We were looking at innovative technologies to better predict carcass yield and kind of thinking, much bigger and broader than maybe what our industry had thought of before. And so starting to ask ourselves questions of what is yield and how do we define yield and what metric is perhaps the most precise and accurate to measure. Charlie Murphy built the yield grade around percentage boneless, closely trimmed retail cuts, but we know that every time we take a knife to a piece of meat, we change it, even if it's the same piece of meat. It's very hard to get a repeatable outcome when we're measuring our outputs from knife work. So what more can we measure? We look to other industries, we look to other countries where they're using things like CAT scanning, and they're running entire bores through these CAT scanners in Spain to measure lean meat yield. They're doing the same thing with sheep in Australia. They're identifying replacements for their seed stock herd to maximize these traits that are important in their industries. And so, can we do that in cattle? So this is a study that I got funded from a number of industry partners in the Pacific Northwest while I was at WSU, and I call it kind of the 100-head study, where we CT scanned 100 carcasses that were highly divergent in biological type. We did have a few dairy crosses in the mix, so some steers, some heifers, some cows. We fabricated those carcasses into 9 pieces that were basically small enough to fit through the gantry of a CT scanner. And so and I'm going to describe why we chose CT and why CT works here in a second. But you can see the clarity of those images on the right-hand side of the screen here from those cuts. And so pretty meaningful study, a lot of data collected from these CT scanners and a lot of data processing that goes into the backside of getting the raw data from these images. So this is why CT, this is how it works. So what we're measuring from the scanner is it's emitting X-rays. Those X-rays are passing through the tissues of each of those cuts, and those X-rays attenuate or absorb into muscle, fat, and bone at differing rates. And the reason why is because muscle, fat, and bone have different densities. And so this measure of Hounsfield unit on the x-axis here is some reflection of a density value. And so you can see that as you move further left on this plot towards a negative 1,000 Hounsfield unit, you're closer to air, which would have a density of 0. So you move towards a Hounsfield unit of 0, that is a density of 1, which is a typical substance would have a density of 1 is water. We know that, again, if a substance sinks in water like fat would, it's less dense. If it sinks, it's more dense, and if it floats, it's less dense. And so as we move further right on this spectrum, we get into the muscle and then the bone category. Again, tissues that are more dense than water and would sink. And we get up into like cortical bone would have a Hounsfield unit of 1,000. So this is why X-ray technologies or CT scans work. This is a depiction of the raw data that we get from a cut, for example, from the rib. And so you've got the spectrum of Hounsfield units here, and then we've been able to, at each Hounsfield unit, mask these different tissues, and then sum the various pixels at each Hounsfield unit to come up with an overall abundance. And so you can see that those Hounsfield units less than 0 there would represent the fat mask. You've got the green, which kind of be 0 from about 150 Hounsfield unit would represent the muscle mask, and then bone would be out there on the far end. So the point is that it's a very effective way to separate these carcass tissues in their pure form, again, and without having to take a knife to that cut of meat. It's very repeatable, it's non-invasive, and I think gives us a lot of hope to trying to predict something with a high level of precision. So this is just another depiction of what the data would look like on a granular level. This is kind of just more of some sketch work in Excel. Again, we're looking pixel by pixel and classifying each pixel based on its Hounsfield unit into fat, lean, or bone. Another real-time representation of what the corner of a ribeye roll might look like, where we have some juncture of some seam fat, some bone. So very pixelated, but again, the size of these pixels is quite granular at 1 millimeter by 1 millimeter by 8 millimeters. So does it work, or why are we chasing this? Again, all with an aim of having a better output that has a greater level of precision and accuracy. Again, maybe isn't entirely applicable in a plant setting, but we're going to talk about some technologies that are here in a second and that we've effectively used to predict carcass composition by CT. So this is the actual weight of those 9 cuts that I showed on one of those first slides there relative to the CT work. So we weighed the entire cut. For example, we weighed the entire clod before we packaged it. And then we scanned the entire clod through the CT scanner. And then this shows the difference, the mean absolute error across all of those 100 head or 97 head of cattle in the study. I just draw your attention to the carcass side here, the summation of all those different components. You can see that the average absolute error is 1.4 pounds or less than 1%. And so as we talk about conducting yield studies, having an error rate less than 1% is critical in maintaining those carcasses in the study to make sure that we've weighed up everything. And the point is that CT is doing that to a very, very high degree of accuracy. You also see the reference density values there on the bottom. So those are the actual density values of all of the tissues in the carcass. And so we just simply done that by the weight of that tissue divided by the volume. And those 3 values of fat, muscle, and bone would be very congruent and consistent for those same tissue densities that have been previously reported in literature for decades. And so we can have a great deal of confidence that CT works, at least to predict weight. But now what about composition? Again, that's the whole point, is even at a fixed weight, can CT accurately differentiate between muscle, fat, and bone? And so to test that, we subset those 97 carcasses into 38. And from those 38, we pulled just the round. We boned the round out. We ground all of the fat and muscle tissue from those rounds. From that ground tissue, that homogenate, we then ran, which kind of is the standard in our meat science discipline for proximate composition of a chloroform methanol fat extraction, and these are the results here. So what we're doing here is measuring the relationship between muscle, fat, and bone composition of the round measured by CT. So that's represented on the x-axis here. So the values we get from the CT machine, again, unaltered. We haven't corrected anything or applied any linear regression correction here. And then on the y-axis are the actual percentages of muscle, fat, and bone from the chemical dissection that I just showed on the previous slide. And the point is that these data demonstrate that, in fact, CT is a gold standard measure of carcass composition for muscle, fat, and bone. And you see R squared values greater than 95%. and mean absolute error rates less than 0.7%. So we can have a great deal of confidence in the use of this technology as a gold standard for measuring carcass composition, and then ultimately, building predictive technologies that can operate in real time to predict that composition. And so that's what we did at the front end of this study. So what I didn't mention before we slaughtered all of those cattle is just in kind of thinking through what technologies exist on the market that, or at least in research and development phases, that might allow us to use things that we know in the case of carcass morphology or cattle morphology to predict carcass yield, much like the yield grade was designed in 1960 to do. And so before we slaughtered all of those 97 head of cattle, we ran them through a SIZAR unit. So this is a millimeter radar system. It's got approximately 70 sensors around its circumference. It sits on the outside of a chute system. Those 70 sensors are firing about 60 to 70 times a second. It takes about 1 second from an animal to pass through from nose to tail. And so you can very accurately collect a lot of data in a short amount of time at the speed of processing, whether this be at a feed yard or a packer. And again, the reason why we did it on the live side was just to see how far reaching we could create these prediction models, just to even see if there was proof of concept in this work. These are what the data look like. So this is on the left-hand panel, you can see this is as the animal's walking through the system. We're shooting this radar, these sound waves. It's hitting the animal and then bouncing back to the sensor, and the amount of time is being computed into a distance. And then we're computing that distance into a 3D point cloud here on the right. So the purple dots would represent the forequarter or the chuck of the animal, or the shoulder region. You'd have the spring of rib represented by the green dots, and then the rump region or the quarter represented by the red dots. So then we use that data that you saw on the right-hand side there to predict the composition measured by CT from those same carcasses. And we do that through a series of very complex calculations here. So this is a neural network that we built. We've solicited the assistance of our group here on campus in our computer science department. So they create a neural network where the input layer is the 3D data that I just showed there. We're basically voxelizing the point cloud and then putting each of those points into an input layer. Goes through a series of functions to predict the output, which is percentage fat, muscle, and bone. And these are the results. So again, running the point cloud through a three-dimensional convolutionalized neural network to predict muscle, fat, and bone on the back end. And we've generated R-squared values of greater than 85%. And we've gotten our root mean squared error down to around 3% or less. And so this just demonstrated proof of concept that that technology exists to measure morphology of cattle in real time, to predict composition, at least that composition measured by CT in this case, and we can do that. Now, this still needs to be validated. We need additional cattle to be scanned, both with CT and with a system like SIZAR to measure morphology. You always have to test every model with a validation set, but this at least demonstrates promise at the early findings of these works. Some other things we're doing in the process here is creating new or virtual cattle, if you will. So this is a technique called data augmentation. What this allows us to do is to increase our sample size in a biologically full meaning way. And so we do that by, because we've collected so much data, just shifting data from a multitude of animals. So building a distribution and then shifting different regions of that animal based on the biological variation within that region to create a new animal. So basically exchanging part for part across all different regions of the animal. And so this is one technique that we've used, is augmentation by distortion, where basically you can take the original point cloud represented in the middle, you can make it fat and thick by squeezing down the points and stretching them out, or make it lean and thin by squeezing in the middles and increasing the height of the animal. And then you can get a different result in terms of composition because you've built the model using these augmented data. So again, these are on point clouds of live cattle that can be captured in real time. My colleague and mentor here is Dale Warner. He's done an extensive amount of work as well on doing the same thing with the carcass. So taking a 3D image, a LiDAR camera image of a carcass, which is a much higher density of data, and then they're predicting the subprimal yield from those 3D point clouds of the carcasses, and they've been able to do that very effectively. All to say that there's promise when it comes to developing predictive technologies for carcass yield, not just for beef on dairy cattle, but for all cattle in our industry, such that we might become more efficient in the inputs that we're putting into our industry, the corn and the water that we're using to produce beef products, such that we can better measure that when it gets to the packing plant and not solely rely on carcass weight, which may be artificially increased solely by increasing the amount of fat that we put on the exterior of the carcass. So we know that the carcass yield is a value proposition opportunity for beef on dairy cattle. Certainly, they're slightly deficient on average relative to the native beef animal. We know that we can select for beef on dairy crosses to be just as, if not higher yielding than native beef cattle with the right kind of terminal genetics. And so that's where we didn't talk a ton about genetics here, but I do think that bull selection is highly critical, particularly for these terminal traits in making the optimal beef on dairy cross. I would guard producers against over fattening those crosses, making sure that we're not feeding them really past 0.6 of an inch of back fat. Again, when you do that, you're feeding out any yield advantage that they may have had over the native beef animal from the get-go. And we know that when the beef herd rebuilds, that these traits, like carcass yield, will become more important to packers. And we also know that at that point in time, animals that are more muscling deficient or deficient from a red meat yield standpoint going into the supply chain, like those with dairy influenced genetics, they will be penalized. And so, where they may not be penalized as much today, or if at all, for this trait, when the beef herd rebuilds and a higher supply of cattle that more adequately meet those needs from a yield standpoint are available, those cattle that are deficient will be penalized. So again, traditional carcass measurements do not accurately reflect carcass yield, and so we know that a trait like ribeye area is not effective when it comes to selection of dairy crosses for muscle. We know that there's tools that allow us to measure carcass composition very rapidly, accurately, and that's non-invasive and relatively cheap in comparison to the old school method of measuring carcass composition, which was the cut and weigh study. And so to that point, our group has purchased a mobile CT scanning trailer here. So this iExact entity is something that Dr. Warner and I and another partner own as a company. And so this is a trailer being built right now with the largest CT scanner available on the market. You can see the standard CT is depicted on the left. The largest one available is shown there on the bottom right. That's the one that's going into our trailer. That will hit the road this fall. We have studies at packing plants being lined up as we speak to start cutting carcasses and start CT scanning those carcasses. And we also know that technology, things that are measuring morphology, whether of the carcass or the live animal, can be developed to predict carcass yield in real time, and we've demonstrated that through our neural networks. Say all of that to say that as we move into an era where we are focusing on carcass yield, whether that be in the dairy crosses or the native beef population, that I'm not suggesting that we sacrifice marbling in doing so, that beef will always and be a superior protein because of its eating quality attributes. What I am saying, though, is that we can do those things simultaneously. We can have cattle that have a high degree of marbling, that eat extraordinarily well, and are producing a high abundance of red meat yield. So that's the conclusion of my study. I understand we've got maybe 10, 15 minutes here for questions.
Yes, thank you very much, Dr. Foraker. Folks, if you want to type in a question in the chat box, or we're down to a small enough number if you want to unmute and ask a question, go ahead and do this. We'll give it just a second to see what questions come in. While we're waiting, all of these experiments you have done with the carcasses, they're Holstein genetics for the dairy base, or have you looked at other dairy breeds?
Yeah, so the predominance of the dam genetics presented in the yield study would be Holstein. And so we would expect a Jersey influence to be lower yielding and require greater supplement from the terminal side when it comes to carcass yield. Albeit, I mean, I've seen many beef dairy crosses that were dammed by Hojo cows or cross cows that were quite superior from a meat yield standpoint. So that brings up the question, Fred. I saw, I think you had conducted maybe a webinar uh, a couple months ago on dairy cow conformation. And so I have been asked the question, is there a point in time when the dairy cow is selected conformationally, not just for milk production, but also for beef production? And I would say if there's any industry to figure that out and how to do that adequately without screwing up their primary bottom line of milk production, it's the dairy industry because they have such exhaustive records. I do think it's possible to build an ideal dairy cow phenotype both for milk production and meat production.
Do you think these results will be skewed as we see more crossbred animals in the dairy industry? The Pro Cross, which is a 3-breed cross, do you think that will change things?
What is the third breed?
The Dane, the Holstein, and I'm drawing a complete blank. Maybe someone can help me out there in the group. Montpelier.
Okay. Well, I would just say that we know that there are breed differences on things like yield, and so I think all the more reason where in a crossbreeding scenario, when I'm saying crossbreeding, I'm saying beef on dairy crossbreeding scenario, that the terminal sire selection becomes just that much more important because you're really only going to be meeting halfway on those traits. And so if any kind of crossbreeding on the dairy side, a three-way crossbred, makes those animals lighter muscle than per se any one of those individual breeds by themselves from a dam standpoint. It's going to require a greater amount of muscle and yield on the sire standpoint to overcome that deficiency.
Okay, I'm not seeing anything else coming in. We'll give just a second for folks that could unmute and ask a question. Oh, you started into the question here. Do you want to take a guess at the genetic choices dairymen should be considering as they look at the beef? I mean, what traits should they be concentrating on when they go to put the beef on dairy genetics?
Right. So, I mean, obviously, fertility is top of mind, particularly if you're in a conventional AI scenario. But so long as fertility and birth weight are within an acceptable range, and you don't have dystocia problems, which I believe that many of the AI companies have and stud companies have done a very good job of marketing the right kinds of bulls to producers that aren't going to result in dystocia problems, then at that point, maximize them from a terminal selection standpoint. So today, marbling is still very much of value in our industry, and so marbling needs to be top of mind. But relative to this discussion in carcass yield, I think carcasses, one, that are still heavy, but carcasses that are phenotypically going to be muscular. Now, you might say, well, you know, you've just shown us that ribeye area is not an accurate way to do that. And that's so I guess what I'm saying there is that I would not put full stock in a ribeye area EPD and genetically selecting a bull. I would be curious in phenotypically, one, looking at that bull himself and the progeny that he's produced, and do they have thickness in other regions of the carcass beyond just the middle meat to try to maximize those yield characteristics. Again, I can't emphasize enough, though, too, that management of those calves, particularly at the end of the feeding period, is very critical. Again, any yield advantage that a beef on dairy cross may have had is going to be fed out of them if they're fed greater than 6/10 of an inch of back fat.
You have repeated that, and I hope that that is a takeaway that people will remember from today's program. Uh, we'll give just a second here if someone wants to unmute or type in a question. While that's happening, we will send out an email to everybody once the program has been archived there at the i29mu.com. In addition, we will ask folks to take just a minute and click on the evaluation and hopefully answer those 4 questions and get some information we can use to make programs better. Taylor just typed in, how has this affected CAB?
So I guess I'm trying to understand your question there, Taylor, if you're talking specifically about carcass yield, if you're talking about beef on dairy. So I'll try to answer both sides of it. Obviously, beef on dairy has been a very positive thing for certified Angus beef, not only because we know that the products that beef on dairy cattle are producing is extraordinarily tender and has increased shelf life relative to Holstein cattle, but in fact, there's some of our data shows that beef on dairy crosses actually outperform native beef cattle at a constant level of marbling when it comes to traits like tenderness and flavor. The fat is more buttery in flavor, and the steaks are more tender. So that's a very positive thing. These cattle, obviously, many of them are Angus crosses, so they're black-hided, and so they're qualifying phenotypically for certified Angus beef. And in fact, in that study of 600 head, I think it was like 98 or 99% of those cattle were phenotypically A-stamped and qualified for, from a phenotype standpoint, for the certified Angus beef brand. Now, whether they had the other traits, the marbling and the ribeye area to qualify, that's a different story. But we know that generally these cattle exhibit a high degree of marbling. And so CAB has generally benefited greatly from the dairy cross. Now, when it comes to some of the carcass yield traits, just this year, CAB increased their maximum allowable ribeye spec from 16 square inches to 17 square inches to be included into their program. But I think that they're recognizing that these cattle that have really large ribeye areas that maybe don't have muscling in other regions of the carcass are becoming a problem. Particularly as we increase the size of the ribeye, we increase the size of a strip from a food service standpoint, and merchandising steaks at a constant portion size, that can be a real challenge regardless of the breed type, whether that animal's beef on dairy or a native beef animal. And so they're at the table and at the forefront of many of these discussions relative to red meat yield, and as are many of the other breed associations in trying to provide tools to beef seed stock producers to better measure and then ultimately manage the trait that is red meat yield.
Dr. Foraker, thank you very much for the program today and Q&A session here. We appreciate the input and remind folks that it will be available to view there at the i29muu.com. Thank you again. Thanks everybody for attending. We'll look forward to seeing you on the 28th at our next webinar when Dr. Peel from Oklahoma will get into some of the market. Thank you very much. We're closing
Excellent.
out.
Thank you, Fred.